Section: Introduction. In this section, we will discuss recent advancements in transferable learning within classical machine learning domains such as visual recognition and language understanding. Large language models, LLMs, have played a crucial role in these breakthroughs. One successful approach to self-supervised learning involved auto-regressive language modeling through next token prediction using causal mask losses. This method was not only scalable in terms of both web-scale text data and model size but also paved the way for training at scales previously unattainable with traditional supervised learning. By conducting training experiments on smaller scales, researchers were able to predict the properties and functions of models trained on larger scales. These predictions were confirmed by training very large language models like GPT-3/4, Llama, and Mistral on standardized language-based tasks, showcasing high benchmark scores across various task types. LLMs especially excelled in few-shot and zero-shot tasks, surpassing previous state-of-the-art models by significant margins and demonstrating emergent functions like in-context learning. Despite these successes, some studies have raised doubts about the claimed generalization and reasoning abilities of LLMs, pointing out function failures that were inconsistent with their performance on standardized benchmarks. However, it has been observed that many of these failures can be addressed through simple adjustments to prompts or by repeated evaluations using majority voting or self-verification. To further investigate these observations, we introduced a simple problem involving a fictional character named Alice, which can be easily solved by humans using common-sense reasoning. We presented variations of this problem to several state-of-the-art LLMs known for their strong reasoning capabilities. While some models like Claude 3 Opus and GPT-4 occasionally provided correct responses with sound reasoning, most models struggled to answer the simple question accurately. Even when interventions were attempted to correct their mistakes, the models often persisted in providing incorrect answers along with nonsensical explanations. Our findings suggest that the current generation of state-of-the-art LLMs face significant challenges in performing basic reasoning tasks, despite their success in complex real-world applications. We emphasize the need for new benchmarks that can accurately assess the reasoning capabilities of LLMs and urge the scientific community to address this challenge to enhance the current state of language model reasoning. Section Summary. In this section, we explore the role of large language models, LLMs, in transferable learning, particularly in self-supervised learning through auto-regressive language modeling. While LLMs like GPT-3/4 have shown exceptional performance in various tasks, recent studies have raised concerns about their reasoning capabilities, as evidenced by their struggles in solving simple problems like the Alice in Wonderland problem. This highlights a discrepancy between the model's performance on standardized benchmarks and their actual reasoning abilities, urging the need for new benchmarks to accurately assess and improve LLMs' reasoning skills. Section: Methods and Experiment Setup. In this section, we aimed to find a straightforward reasoning task that could challenge language models. We explored tasks designed for 7 to 10-year-old students, similar to math Olympiad problems for young children. These tasks require basic reasoning skills but are not overly complex. We created a simple problem where Alice has a certain number of brothers and sisters, and we need to determine how many sisters Alice's brother has. This problem, called the AIW problem, can be solved using common sense by considering that all siblings share the same parents. The solution involves adding the number of sisters Alice has to 1, giving us the number of sisters her brother has. Initially, we thought that this problem would be easy for advanced language models. However, when we tested them with specific values for the number of brothers and sisters, we found that most models struggled to provide the correct answer. The models often relied on basic arithmetic operations instead of logical reasoning. By experimenting with different variations of the AIW problem, we created 4 instances with varying numbers of brothers and sisters to test the model's reasoning abilities. To evaluate the model's performance, we needed a way to extract and compare their responses. We added a clear instruction for the models to provide their final answer in a specific format. This allowed us to parse the responses easily and determine if they were correct. By conducting multiple trials with different prompts, we could assess the model's ability to reason correctly. Prompt engineering, where the way a question is presented can affect the model's response, is crucial. We developed 3 prompt types: standard, thinking, and restricted, each influencing the model's behavior differently. The standard prompt asked for the solution without any specific requirements. The thinking prompt encouraged careful consideration, while the restricted prompt limited the output to just the final answer. We observed that the model's responses varied based on the prompt type used. By using different prompt types and variations of the AIW problem, we could analyze the model's behavior in various scenarios, such as incorrect reasoning, overconfidence, and learning within context. Section Summary. In this section, we devised a simple common-sense reasoning task, the AIW problem, inspired by elementary school math Olympiad tasks, to test the basic reasoning abilities of language models. Surprisingly, state-of-the-art models struggled to correctly solve the problem instances we created, indicating a gap in their reasoning capabilities. By evaluating model responses using a beta binomial distribution, we were able to estimate correct response rates and compare the performance of different models, highlighting the impact of prompt types on model behavior and response quality. Section: Selecting models for evaluation and conducting experiments. In this section, we select models for evaluation and conduct experiments. We aim to test the latest models that claim strong reasoning abilities, supported by high scores on standardized benchmarks that assess problem-solving and reasoning skills. We choose well-known models in the machine learning community, listed in the supplementary table, which also perform well on popular leaderboards like OpenLLM by Hugging Face or Elo by LMSWise. These models vary in size, from small to large, to understand how their problem-solving abilities change with scale. After selecting the models, we run experiments by presenting them with a set of prompts containing AIW problem variations. We use platforms with API access to these models and automate the process by scripting the necessary routines to prompt the models. The routines are straightforward and can be used by anyone with access to the APIs or locally hosted models. We record all interactions with the models for community verification. The data collected is then analyzed to determine the model's accuracy rates in responding to the prompts. We also categorize prompts into standard, thinking, and restricted types to observe how the model's responses differ based on the computational resources they use. Each model undergoes at least 30 trials for each AIW variation and prompt type. We also include control experiments using different prompts to compare base models' responses with instruction-based models and to assess model confidence estimation and self-correction attempts. We then evaluate the performance of selected models on the AIW problem. Most models struggle with this problem, with many failing to provide correct responses, and the majority achieving correct response rates below 0.2. The exceptions are the largest closed models, GPT-4 and Claude 3 Opus, which achieve correct response rates above 0.3. Smaller scale models like Mistral 7B, Mixtral, Qwen, Command R+, and DBRX Instruct, as well as larger scale open weights models, fall behind in performance. The results show correct response rates for different prompt types, highlighting the impact of prompt restrictions on response quality. Models like GPT-4o and Claude 3 Opus stand out as top performers, while older models like Llama 270B Chat also show strong reasoning abilities. Some models provide correct answers through proper reasoning, while others arrive at the correct answer through incorrect reasoning. We observe fluctuations in response rates across different AIW variations and prompt types. Furthermore, we compare the model's performance on standardized benchmarks like MMLU, ARC, and HelloSwag with their performance on the AIW problem. We find a mismatch between high scores on standardized benchmarks and actual performance on the AIW problem, indicating that the benchmarks may not accurately assess basic reasoning abilities. This discrepancy complicates model comparisons and predictions based on benchmark scores. Smaller-scale models trained on large token budgets struggle with the AIW problem, while larger-scale models like Llama 270B, GPT-4, and Claude 3 Opus show better performance. Section Summary. In this section, we select state-of-the-art models known for strong reasoning capabilities and evaluate their performance on standardized benchmarks like OpenLLM and Elo leaderboards. By exposing these models to AIW problem variations through different prompts, we observe that most models struggle with reasoning tasks, except for the largest scale models like GPT-4 and Claude 3 Opus, which show higher correct response rates. Interestingly, smaller scale models that perform well on standardized benchmarks often fail on the AIW problem, highlighting a discrepancy between benchmark scores and actual reasoning capabilities. Section: Curiouser and Curiouser. In this section, we delved deeper into the failures of state-of-the-art language model, LLM, models that claim to have strong capabilities. We explored different aspects of these failures and highlighted the most significant ones. One key finding was the discovery of a more challenging problem formulation called AIW+ that proved to be even more difficult for all the top models we tested. When we presented these models with the AIW+ problem, we noticed a significant drop in their performance across the board. We were particularly intrigued by the model's explanations for their incorrect solutions. For a prompt type like thinking, where the models were asked to double-check their answers, we observed instances where the models confidently asserted the quality and correctness of their wrong solutions. They used phrases like, "logic holds up," "no mistakes in the reasoning," and "solution is correct," to support their incorrect answers. This overconfidence was consistent across various prompt types like scientist and confidence, where models continued to exhibit unwarranted certainty in the quality of their solutions. Furthermore, we observed that many models, despite providing incorrect answers, generated elaborate explanations filled with seemingly logical statements to justify their nonsensical solutions. We termed these explanations as confabulations. Some models even incorporated concepts like gender identity or social norms into their confabulations to bolster their incorrect reasoning. To push the models to their limits, we introduced a more challenging problem called AIW+. This new problem retained the logic of the original AIW but included additional complexities in describing family structures. The performance of the models plummeted even further when faced with the AIW+ problem, with some models experiencing a near-complete collapse in their functionality. Additionally, we conducted experiments to understand the model's inability to correct their mistakes, their struggles with relational SQL database formats, and their failure to handle parameterized versions of the AIW problem. Despite our efforts to guide the models through multi-turn interactions and customized prompts, most models consistently failed to revise their incorrect solutions or adapt to the variations of the AIW problem. Overall, our findings shed light on the limitations and shortcomings of these advanced language models, revealing their struggles with complex reasoning tasks and their tendency towards overconfidence in the face of incorrect solutions. Section Summary. In this section, we explore the failures of state-of-the-art language models in solving complex reasoning tasks, particularly the AIW+ problem, which proved to be even more challenging for these models, leading to a significant drop in performance. We also observe a concerning trend of these models exhibiting overconfidence in their incorrect solutions, often providing persuasive explanations to justify their erroneous reasoning, a phenomenon referred to as confabulations. Additionally, we introduce experiments that shed light on the limitations of these models, such as their inability to revise wrong solutions and their struggles in reformulating problems into relational SQL database formats. Section: Related work and limitations. In this section, we discuss the related work and limitations. We have seen that measuring the capabilities of large language models, LLMs, has become crucial after the significant advancements in language modeling. Evaluating and comparing models require various standardized reasoning benchmarks to assess how well a language model can reason. These benchmarks, such as ARC, PIQA, GSM-8K, HelloSwag, MMLU, and Wino Grande, are categorized based on the specific reasoning abilities they aim to test. Several efforts have been made to enhance the reasoning performance of LLMs based on these standardized benchmarks. However, concerns have been raised about the discrepancy between the claimed capabilities of LLMs, as measured by benchmarks, and their actual reasoning skills. Some studies have highlighted instances where models fail to demonstrate effective reasoning abilities, prompting the need for more challenging benchmarks like Helm or Big Bench. These new benchmarks are designed to evaluate the generalization capabilities of models beyond mere memorization. Our work is aligned with these efforts and aims to reveal breakdowns in language models' reasoning abilities, particularly in scenarios where models struggle with variations in problem formulation. While previous studies have focused on specific reasoning failures, such as challenges in causality inference, we focus on a common-sense problem with a straightforward structure to highlight deficiencies in basic reasoning skills. One limitation of our current approach is the lack of diversity in the variations of the AIW, artificial intelligence and the web, problems we consider. To address this limitation, future work could focus on systematically generating instances to evaluate a broader range of responses.